Hi, everyone. My name is Shaoor Munir, and today I'll be presenting our work on cookie graph, which is a novel technique to measure and counter use of first-party cookies for tracking. This work is a joint collaboration between researchers from University of California, Davis, EPFL, and University of Washington. Before going into details about the measurements that we conducted and some of our results, allow me to first give a quick overview of what are first and third-party cookies and how are they used for tracking. Cookies were introduced back in 1994 when Netscape wanted to build a mechanism to know which users were repeat visitors of their shopping site. The introduction of cookies allowed Netscape to set a session identifier which remained consistent across different visits of the same user. The important thing to note here is that cookies were meant to be used for the first party only. However, the way that they were designed allowed third parties present on the site to also set them and retrieve them on other sites. So for example, if a user visited New York Times and Criteo sets a cookie with a unique user identifier, the same party present on a different site like TMZ can also get that cookie and read the same user identifier to know that it is the same user visiting both sites. Because of this oversight, third-party cookies allow easy cross-site tracking. The debate around allowing third-party cookies to exist and track users started right after their introduction. There were a number of different proposals studied to curtail the impact of cross-site tracking through these cookies, but none of them really stuck the landing. Safari ultimately became one of the first browsers which had some restrictions on third-party cookies by default when it was introduced in 2003. And with ITP 2.3 in 2018, it completely blocked third-party cookies. Currently, Firefox partitions third-party cookies by default, which means that although third-party cookies are allowed to be set, their values are only available on the site they were originally set on, which renders them unusable for cross-site tracking. Google Chrome, on the other hand, does not have any restrictions against third-party cookies, but their aim, at least at the time when I started this presentation, was to block third-party cookies by 2024. But we still have around 10-15 minutes left, so they might push it back another year. Let's hope so. Okay. Anyways, considering that third-party cookies are going to be blocked on majority of browsers within a year or two, depending on how Google Chrome behaves, the question arises that what these trackers will use for cross-site tracking now. Here we look at a few different ways they can use to track users and some of their shortcomings. Firstly, they can collect fingerprints from users that visit their website. This is a classic tracking technique in which different signals about the user, which can include their location, IP address, device information, etc., are collected across different sites in an attempt to determine the same user's presence on those sites. While these signals are accessible across different sites, they're relatively inaccurate, as two users might have very similar signals, or the same user might have different signals if there's a significant time difference between their collection. Trackers can also attempt to collude with a first party to store a first-party cookie once a user visits a website. This cookie will remain in the browser as long as the user does not manually clear them. But that information will not be accessible across sites, thus reducing their effectiveness for cross-site tracking. And lastly, trackers can collaborate with the first parties to obtain some first-party data about the visiting user. This can include information like email addresses and their phone numbers. If the tracker is able to collaborate with enough first-party publishers to get this information, it can be used for tracking users across different sites. And because users are unlikely to switch their email address or phone number too frequently, this will remain stable over a longer period of time. However, this method requires a lot of first-party to first-party collaboration, which might not be feasible for most trackers. So if there's no one good solution, are trackers making use of a combination of these techniques? If so, then how can we go about detecting that? This is what we attempted to answer with our measurement study. We designed a measurement to detect increased usage of first-party cookies once third-party cookies were blocked. Our intuition was that forcing the trackers to use methods other than third-party cookies will reveal the behaviors and patterns that they are planning to use in the face of a widespread third-party cookie blockage. We ran this experiment on a mixture of top 1,000 sites and 9,000 sampled from low-ranked websites. And sure enough, we discovered some interesting cases where trackers showed increased first-party cookie usage once we blocked third-party cookies. Even though third-party cookies were completely blocked, Criteo, which is a very well-known tracker, its cookie CTO bundle was found to be set as a first-party cookie on 132 news websites. And this was after blocking third-party cookies. Similarly, Lotami and ID5, which is a new and upcoming user tracking service, they were found on 24 and 25 new sites respectively. And once we had found these interesting cases and parties making use of first-party cookies, we analyzed their documentation further to exactly figure out how they were using these cookies for tracking. PTO, ID5, and Lotami, all of them advertise their new cookie-less solutions, which do not rely on third-party cookies. They claim about creating a graph which takes in information about the user and churn out an ID which can be used universally across different sites and devices. We found that these IDs were ultimately being set in first-party cookies. So with the help of this documentation, and then looking at the behavior of these parties and the cookies in our data set, we formalized how first-party cookie-based tracking was actually taking place. So what we found was that trackers collaborate with first parties to run their code in a first-party context. What this means is that if third-party scripts are embedded in the main website frame, then the script is not restricted by the same origin policy. And this allows these third parties to both read and write first-party cookies. Once these trackers are running in a first-party context, they can also collect fingerprintable data from the website, which can include location, IP addresses, operating system, etc., along with some identifiers like the names, username, email addresses, and phone numbers, and combine that data to determine the user's identity. This identity is stored in a first-party cookie and then later shared with other advertisers and trackers. So with the help of this documentation and then analysis of these behaviors, we formalize some of the key behaviors of first-party tracking cookies. And these behaviors are multiple scripts reading and setting first-party cookies, their values being sent out to different endpoints, and then also the cookie value itself being set from a response value. The response in this case would come from an identity resolution service, which is run by these trackers. And because it is not feasible to block all first-party cookies, as a large number of them are indeed set by the website itself, and then are used for valid functional purposes, we decided to make use of these key features to train an ML model, which can isolate tracking cookies from functional cookies. To build that model, we first crawl 10,000 different sites using an instrumented Firefox browser. We collect interactions between different elements on the web page and extract the relevant features. We then create a graph representation of these features and interactions, which is then labeled by combining data from Cookiepedia, which is an online service collecting information about the purpose of cookies declared by the sites themselves, and filter lists, which label the setters of those cookies as either tracking or non-tracking. Finally, we feed this data to an ML model, which is then trained to classify if a given cookie, given first-party cookie is tracking or non-tracking. Now coming towards some of the results from our evaluation of this trained model. We compared the results of our classifier with two other approaches to restrict cookies. The first one is cookie block, which uses a combination of name and value features to determine the purpose of a cookie. It works for both third and first party cookies. While the other is all the amazing filter lists, some of which are created by the people listening to this talk today. These can block tracking scripts and requests, but they can also indirectly block cookies set by these resources. We made use of WebGraph in our analysis and calculated the list of cookies which it blocked and used it for comparison with our approach. We compared COOKIEGRAPH against these approaches in three different categories: the overall accuracy, the website breakage, and finally robustness to cookie name changes. Looking at pure accuracy numbers, COOKIEGRAPH outperforms both filter lists and cookie block by at least 10%. Important point to note here is the massive difference in precision among these approaches. Having a higher precision means that COOKIEGRAPH is less likely to produce false positives as compared to other two approaches. Naturally, we expect the higher false positive rates of other approaches to mistakenly block functional cookies and thus result in website breakage, which we study next with our breakage analysis. We know from the example of Safari and Firefox that restricting for third-party cookies is possible, but it is also logical to assume that because first-party cookies are being set by the site itself, blocking them would be much more challenging. We also wanted to measure if we can actually block first-party cookies without incurring significant website breakage. So we designed an experiment to compare breakage across all three approaches on 50 different sites. To cover different kinds of breakage that can happen, we divided our analysis into 4 different categories. Navigation, which involves moving across different pages of the site. SSO, which can include logins from third-party services like Facebook and Google. Appearance of the website. And finally, the additional functionality, which can include cart functionality, chatbots, the dark mode switches, etc. We also categorize breakage as either minor or major. A breakage is considered as major when the user is unable to use the functionality, while it is classified as minor if it only makes the usage of that functionality a little bit more complicated. Well, it turns out that if you selectively block first-party cookies based on the behavior like cookie graph, you only get minor breakage on 2% of the sites, while other approaches like cookie block result in major breakage on 10% of sites. And using filter lists can cause minor breakage on 4% of sites and major breakage on 10% of the sites. This clearly shows that not only is blocking first-party cookies feasible, it is arguably a better approach than completely blocking scripts and network requests responsible for setting these cookies. In the ad blocking community, we are also aware that trackers will always try to circumvent any restriction placed on them. We have seen these approaches in URL blockage, where the same tracking code is served through different URLs to circumvent blockage. So we wanted to see if trivially changing cookie names is something trackers can use to evade detection when we started blocking first-party cookies. We did this by comparing robustness across these different approaches by changing the cookie names and then rerunning the analysis. As COOKIEGRAPH does not use any name features and only relies on the behavior of cookies, there is no drop in performance due to this evasion attempt. On the other hand, cookie block directly relies on matching the cookie name with the top tracking cookies. This approach leads to 15.68% drop in cookie block's performance by just changing cookie names. This shows us that COOKIEGRAPH's approach is resilient to trivial attempts by trackers to evade detection. Now that we have a reliable ML model, we can conduct a large-scale study of trackers. And we do so by running COOKIEGRAPH on an unseen dataset of top 10,000 websites. Next, we will see some interesting results that we observed by deploying COOKIEGRAPH in the wild. Firstly, looking at the percentage of sites which are using first-party tracking cookies, our analysis shows that only 6.57% of sites are not using any first-party tracking cookies, while the rest of the 93.43% of the sites are using at least one first-party tracking cookie. This shows that first-party cookies are widely being used for tracking among top websites. And with the upcoming restrictions on third-party cookies, we expect this number to go even higher from this point onwards. Of all the first-party tracking cookies that are in use, 98.39% of them are set by third-party scripts, which are embedded in a first-party context. Considering that this requires a third-party script in a first party's main context, this large-scale collaboration between publishers and trackers comes as a surprise. And it also opens up the first party to unknown and untested code, which can be freely abused by third parties. We also found out that 41.55% of all the first-party tracking cookies which were set, they were set by scripts which are included from domains known to be involved in fingerprinting. This also shows that these cookies are being used in conjunction with some other pervasive tracking technologies like fingerprinting. This whole situation becomes even more concerning by the fact that once these cookies are set, they are also sent out to a huge number of other trackers and advertisers. In this slide, we look at the distribution and shading of a few top first-party tracking cookies. Google's own first-party cookie, which is present on nearly 2/3 of all websites, is being shared with 179 other domains. Similarly, for Facebook's first-party cookie, which is present on 33% of the sites, is shared with 73 other domains. Microsoft's tracking cookie are present on 10% of the sites and are then shared to 15 and 21 other domains. While Criteo, which is a very well-known tracker, sets its first-party cookie on nearly 6% of the sites and then shares it to 7 other domains. This excessive distribution of first-party cookies show that there is a big part of information sharing chains that exist between different trackers and advertisers. Take example of Yandex, HubSpot, and QuantServe. Even on their own, they are considered to be among the biggest online trackers. The extent of their tracking capabilities increase manifold when we consider the fact that their first-party cookies are being shared with other massive trackers like Google, Taboola, Facebook, Criteo, and PubMatic. So these first-party cookies enable a wide network of information sharing that currently exists without any strong oversight and preventive measures. So in conclusion, our study has shown that first-party cookies play an important role in the next stage of online tracking, and we believe that it is imperative to include protection against first-party cookies in any next-gen ad blockers and filters which aim to ensure that users control their own online presence. As a community, we have a strong history of using filter lists to block tracking resources. Our results have clearly shown that it is indeed possible to not only detect, isolate, and block first-party tracking cookies without causing any major website breakage. It is actually a more user-friendly approach to restrict tracking activity. At the moment, there is no space for cookies in our popular filter list. There is some effort on part of uBlock region to block cookies set by a particular domain, but we believe that a more concentrated effort is definitely needed to counter this rise of first-party tracking cookies. Thank you for listening to my presentation, and I'm looking forward to answering any questions that you might have.